Welcome today to the webcast titled Vital Statistics of Distribution Assets from AMI Meter Data, presented by Robert Sonderegger, Director and Engineering Advisor for Itron. Robert?
Good morning, everyone. I assume everybody can hear me, and if not, please speak up. Today, I'm going to talk about work in progress at Itron that I'm involved in. So some of the issues I will speak about are done and dried, and others are work in progress. Specifically, I'd like to speak about some technical data, some technical information that we can get from analyzing some AMI data. And I will make three examples. One is of how to use correlation of meter voltage changes to validate meter-to-transformer connectivity. Another one is a novel approach to theft detection. And the final one, if we get to it, if we don't run out of time, is how to use a post-mortem evaluation of outage events to also get to grid topology. First example is how to correlate meter voltage changes to validate meter-to-transformer connectivity, or grid topology. Why do we care? Grid topology, or specifically connectivity, has become quite an important subject because almost no analytics can be done correctly if we don't know exactly which meter is attached to which transformer, and also to some extent which transformer to feeders. While transformer to feeders tend to be documented pretty well, meter-to-transformer connectivity, while usually documented at a utility, is frequently out of date, and which introduces quite a few problems. So it's difficult to do decent TLM or otherwise know how to manage equipment if you're not sure exactly what load is on what transformer. An existing method to get to meter-to-transformer connectivity is visually tracing lines to transformers if they're overhead, or sometimes you can send and receive signals that send through specific service drops. And of course, you could always ideally keep very accurate records and make sure that every change in the field is properly entered into the utility systems, but we're all human and that doesn't always happen, and understandably line personnel may be more concerned about their safety than getting every last information always in place. So all of these methods are quite labor intensive. We've recently developed a new method that looks for correlation of voltage changes across meters that are within a reasonable distance of each other to either validate or disprove that the meters are connected to the same transformer. To do so, we need 5-minute interval data from voltage for several weeks. Doesn't mean you need 5 minutes forever, but for a while you need 5-minute interval data. Here is a typical trace of 5-minute interval data, and on the top graph you see in blue the actual voltage over a period of about a week, and on the bottom the orange line are corresponding kVA values. The voltage is actually upside down simply because it tends to be, by and large, counter-cyclical to the kVA, so that you can see some of the regularities. Some of kVA causes voltage spikes, but many voltage variations are caused by other than the kVA on the meter. They're caused by secondary line fluctuations. I'm presenting both voltage and kVA because in the later example we'll need both. Right now we're only going to focus on voltage, which is the blue line. Below, in the graph below, you're seeing the exact same data but rather than absolute voltage and absolute kVA, you only see the changes therein. You only see changes from 5 minutes to the next 5 minutes. So it's basically delta volts over 5 minutes. It's basically a first derivative. And not surprisingly, all this seasonal up and down or daily up and down is gone, and we are only getting very short-term fluctuations. It's a very low-tech way of a filter. So why do we focus on change in voltage? Because we're really not interested in how the secondary voltages vary. We're only interested in short-term voltage changes. And in fact, the shorter the better. 5 minutes is a compromise between what is technically feasible and what might be even better results, which is even shorter than 5 minutes. But let's focus on 5 minutes right now. So what we found is that the voltage changes correlate quite well for meters that are on the same transformer, not very surprisingly. And they don't correlate well for meters that are on different transformers, especially if the transformers are on different feeders or on different sections. Let's see what these voltage changes actually look like. And we're going to see now a plot of 2 meters that are on the same transformer, and on one axis is 1 meter, and on the other axis is the other meter. And as you can see visually, there's quite a good correlation. The x-axis here shows changes from up to 5 volts, plus minus 5 volts is quite a bit. It's a very active meter. And similarly on the y-axis. And you're seeing that in this particular case, what happens on one meter is pretty much reflected in the other. The reason of the pixelation is simply that the voltage values that we get from these meters have a resolution of 0.3 volt. So it's all kind of digitized this way. Look again at the same kind of correlation, but 2 meters that are on different transformers. And you see right away what happens. There's very poor correlation on meters on different transformers. In the nomenclature here, the ID before the colon indicates the transformer, and the ID after the colon indicates the meter number. So there's very poor correlation. So let's do this a little more scientifically, a little more accurately, and we define the concept of meter affinity. And the meter affinity is simply the Pearson coefficient, or in the vernacular known as the correlation coefficient of the time series of voltage changes. You simply take the voltage changes of 1 meter, which will be Xi, and the voltage change of the other meter, which is Yi, and correlate them with each other. And the X bar and Y bar are the average over long term, which tends to be 0. I mean, voltage changes are almost by definition tend to be 0 over time, when averaged over time, but obviously they're up and down in between. And then again, the cross products at the bottom. This is statistics 101, or even simpler than that. And we're calling this, when applied to 2 meters, as affinity. And we're finding that meters on the same transformers will have affinity as high as 0.95, and meter pairs on different transformers will rarely have affinities greater than 0.5. So how does this work when we do it for a whole lot of meters? First of all, the numbers get kind of big. If you just take n meters and you were to calculate affinity for any 2 pairs without repetition, you get n. It's basically n squared. And that, of course, very rapidly gets too large. For example, for 630 meters, which is one data set that we used, you come up with 187,000 and change affinities. For larger n, it's simple to limit the combinations. It doesn't make any sense to try to correlate 2 meters that are a mile apart. They're very unlikely to be attached to the same transformer. So you can simply limit the bilateral affinity calculation to only include meters that are within some reasonable distance, for example, 1,000 feet. So in the case of another data set that we've recently looked at, which has 13,400 and change meters, we only have to calculate 552,000 affinities, which basically takes almost no time at all. That's, for the computer, that's very simple. The data set for information was about a month long. It's not clear that it had to be a month long, but that was a convenient time. So the closer electrically 2 meters, the higher the mutual affinity. The more distant electrically, the lower the affinity. So now we're going to show all affinities calculated for the data set. And we're seeing, let me explain what this figure here shows. On the left, the orange curve, you're seeing affinities calculated for meters that, according to the utility records, are on different transformers. And the blue line shows the affinity of meters that, according to the same utility records, are on the same transformer. It is a lot more jagged, the blue line, simply because there are fewer numbers. It's on the right-hand side here. And that's not surprisingly. There are many fewer combinations of 2 meters within one transformer than between any one of those meters and all the others that are within a reasonable distance. So you will always have fewer meters that are putatively on the same transformer than those that are not. So what we're seeing right away is that there's a very clear distinction between the 2 groups, those meters that are on different transformers versus those that are on, but there is some overlap. And the overlap could be indicative of some misconnections. In other words, meters that are putatively on one transformer according to utility records, but in reality are not, or are on a different transformer. So let's dig into this a little more. So what we found with a lot of different tests, we found that a good way to validate connectivity, remember the whole exercise here is to validate existing connectivity and correct it where it's found to be wrong. So to validate it, we found the best way is to calculate for each meter the highest affinity with any of its peers. So for example, if you have a meter with 9 transformers, if you have a transformer with 9 meters, for any one of the 9 meters, you calculate the affinity with its 8 peers, so it's 8 numbers, take the highest of that, then do the same thing for all meters that are not on the same transformer, which will be a lot more than 8. It might be a few hundred that are within a reasonable distance. And again, take the highest affinity there and call that away affinity. So you have 2 numbers for each meter, a home affinity and away affinity. If all goes well, the home affinity will usually be considerably higher than the away affinity. And by higher, I mean within statistical significance. Occasionally, it is not, and that is where the meter's topology is likely wrong. In other words, if the away affinity is considerably higher than the home affinity, not only is that meter in the wrong transformer, but we will also know which transformer it really should be connected to. Here is a picture of, in this particular case, 597 meters, where each meter is represented by 1 point, and we show on the same chart the home affinity on the y-axis and the away affinity on the x-axis. So meters that have a high home affinity and a low away affinity, they're fine. So this upper quadrant represents the meters with confirmed topology. And this particular utility is very good at their record keeping, so the great majority of meters are just fine. Here are a few meters, and there are 6 of them, that clearly do not are in the wrong, have been classified wrong. There's no way that a meter can correlate at 0.65 with another meter on another transformer and only at, in fact, slightly negative, which doesn't really mean much, to all the meters on its own transformer. This meter here, I would bet anybody an expensive dinner, is misassigned. And the same for these meters here. There are a few meters that are just kind of on the 45-degree line, and we really can't tell on these. In fact, statistically speaking, if we're using a 95% confidence level, there is a gray area here, which is kind of represented by these dashed lines, where you can't tell. A meter that has approximately the same home affinity of here 0.35 and also 0.35 away affinity, you can't tell what's going on. It's not correlating well. Why would that be? Well, it's possibly that somebody's on vacation, so there's very few voltage changes at all, and so you cannot get much information. So the test will resolve the majority of meters, not necessarily 100%, but you can always repeat this over a different period of time and you get better data. So this connectivity validation method is quite simple. Start with a putative meter to transformer topology. Just start with the utility records, and it doesn't really matter how good they are. It's just a point of starting. Calculate home affinities and away affinities. Look for which ones are greater and which ones are smaller, and you've got your results. It's a process that is pretty quick and is, of course, can be totally automated. It can even be done on a periodic level. And at Itron, we're working on ways to do this even in a distributed manner, so we don't even have to do this centrally anymore. But it doesn't matter where it's done. It's just a matter of convenience. With this, we're going to the next example, which uses similar data. Remember that we looked at both voltage and current. Well, one application that we've looked into is theft detection by comparing voltage levels of a meter to that of other meters on the same transformer. Why would we do that? How do you usually look for theft? Well, one is that if you get frequent tamper flags received from a meter, that may indicate that somebody's fiddling with it, but it could also be utility personnel doing something, or that maybe the meter has something wrong with it. You can also look for abnormally low usage compared to historic usage. But who knows? Maybe those people are on vacation for a few weeks. So none of these tests are surefire, and also they can be pretty intensive, and after all, any individual theft, at least as a resonance, tends to be small. So if you want to be successful, you want to find a whole lot of them as painlessly as possible. So a new method that we've developed is to compare voltage among meters on the same transformer. Well, of course, you need to know which meters are on the same transformer, but we just discussed that. We can be pretty confident that starting with utility records, we can get to a very accurate meter-transformer connectivity. But we also probably need to correct for load on meter. You wouldn't really expect all meters on the same transformer to always have the same voltage. They do vary because of different loads on different meters. So before we go any further, let's find out what kind of thefts we have. So the normal case is the transformer and its meters and the loads are attached to the meters and everything's fine, no problem. One type of theft is a load that is put on the utility side of the meter, or occasionally even on the secondary, An example here is a growing lamp, and I won't mention what is being grown, that may be tapped directly into the service drop. If you do that, you use power, but the meter doesn't record it. Another type of theft is what we call a meter bypass, where you're shunting a wire from the utility side to the customer side of the meter, in which case most of the load goes to that wire, although some will still go to the meter. It has to do with relative impedances. And that's particularly hard to detect because the meter will still record, it just won't record that much. So how do we go after this? Let's go back and look, let's look here at the uncorrected meter voltages of, in this particular case, these are 9 meters on one transformer. 9 meters here, and at the bottom we're seeing a trace which shows the maximum voltage difference from one meter to another. For example, if you're looking at this yellow trace here, which is meter 13433, you might wonder what is going on here. Why is the voltage dropping so much? Well, maybe they're having a big load or something, so that's not inherently suspicious. And there's a lot of variation in these different voltages. And so it's a little hard to use any one deviation and say, aha, these people are using something that we don't know about. So one trick to do this a little better is to eliminate the variation from what we call self-induced. It's a self-induced variation. I'm sorry. Each meter's voltage is a combination of secondary line voltage and its own and the load on that meter. We call that the self-induced variation versus the line variation. So how can we eliminate the self-induced variation from individual loads? Well, we know the loads. We record them at the same time in kVA, but how do we convert kVA loads to voltage drop? Ultimately, that has to do with the service drop impedance. If we knew the service drop impedance, we would know how every kVA, how many fractions of volt or volt that corresponds to in voltage drop. But that's a tall order, and we don't really know the impedance. Well, it turns out there is such, you can do so. And I'm showing again the chart we saw at the beginning of this talk, which shows voltages and kVA, and down here again the changes. It turns out if you correlate the change in voltage to the change in current, you also get often a very nice correlation, as shown right here. In this case, the change in voltage is on the vertical axis here, and the change in load expressed as amps is shown on the x-axis. The orange curve represents the number of intervals in each of these bins. In other words, most of the change in voltage and change in current are very small. That's why this curve peaks around 0. But there are some outliers, and those are the ones that give us the idea of what the impedance could actually be. In order to do the regression here, we actually do an extra little trick. We average the voltage change from given current change bins, so we get a nice regression. I'm sure some statisticians on the call will wonder if this was a good thing to do. And the slope of the line between change in voltage and change in current is exactly the resistance. And in this particular case, it's 54.8 milliohms. We can actually measure an apparent impedance of each service drop by this simple regression, which can be repeated periodically. Once we know that, before I go any further, just for your interest, This is a distribution for about 13,500 meters. No, I'm sorry, I'm wrong. It's a little over 10,000 meters. This is a distribution of the impedances that we found, the apparent impedances. The average is around 50 milliohms, although the most frequent one is less, but there are some tails over here. The blue line is simply the cumulative distribution. So now we can use this impedance to eliminate or at least minimize the self-induced voltage variation simply by, because we know that the load would cause this much voltage change. Each load causes this much load, and I'm sorry, each load causes this much voltage. We subtract that from the voltage that we see, and we can get to what the meter would show as voltage if it had no load at all. Here is the simple equation for it. And if we do that, again, this is the same chart I showed you before. This is the uncorrected voltages. On the next chart, pay attention, the next chart, I'm showing the exact same data, but after subtracting out self-induced voltage. And as you can see, the variation between the different curves is a lot smaller, and the maximum high to low meter variation of voltage is also a lot smaller. So now it's sort of like sharpening a knife. We can tell much better when something is going wrong, because if somebody were to steal power, the voltage would go down, even the voltage would show as being very low, because there's no way to correct for that since it's not measured. So in this particular case, if we use a theft that's caused by spurious load, this is what we would expect. We would expect in this particular case, this is simulated, unfortunately. We have not yet tested this in the field, but if for a 7 kW load, we would expect a significant voltage drop, and it's very easy to see that, and it also would be very easy to detect this automatically. In the other type, in the meter bypass is a little different. The meter bypass can be found in a different way. If it's a permanent bypass, remember this line here where we got the regression on the meter? In a permanent bypass, the slope will be a lot higher because less measured power would cause a change in voltage than when everything was measured. So you would be able to tell by the impedance being unusually high, or if you monitor this continuously, which is what we're suggesting to be doing. We're suggesting that every meter should have continuously monitored impedance. It's a very simple calculation. And if you're seeing a change, you know something has really changed here. And the bypass is the most likely cause, unless, of course, the utility itself has installed new conductors or a conductor to service drop. This is when there's a permanent bypass. If there is a intermittent bypass where they're only switching a bypass on during certain parts of the day, you would see a bad correlation. You would see things all over the place. And you could conceivably refine that by using windows of the day and see if you get a better correlation, but we're getting into labor intensive, and everything we present here is something that should be automatable, should not require actual humans to do it. So that's for our two examples. And the third one, which is unfortunately easier to explain than to show, is how we can use outage events to our advantage and also use them to verify connectivity. We all know that when an outage occurs, AMI meters will transmit the power off signal, but especially in a mesh network, only a subset of those signals will actually make it to the central office, because some of the meters that are in the middle of the outage, while they emitted their last gasp, it will never make it because other meters that are supposed to retransmit are already without power as well. So inevitably, you have an incomplete picture of the meters affected by outage. And the only way to get a full picture of the outage is to use the actual connectivity, which needs to be kept up to date to be able to get to the full extent of the outage. Well, we spoke of one way to get good connectivity using 5-minute interval data, but here is another way which is much lower tech, does not require does not require a 5-minute interval data. In fact, it can probably be done with 15-minute or even hourly interval data, and it's much lower tech. And all it consists of is to systematically look at outage events and basically look which meters went out together and which one didn't. So, we do that by grouping meters by the power outage start timestamp. So if you get a bunch of outages, you look for commonality, those that were out at the same time, and those will tell you which ones are likely on the same transformer or on the same section that went out. Any one outage will only tell you some information, but if you're systematically compiling that information, over time you're building up a pretty good database of meter to transformer connectivity and even transformer to section. In one example, we looked in a utility that had a 240-minute outage with 66 meters affected on 4 transformers. And we found that for one transformer, 19 of 21 meters were in outage. Well, you know pretty well if 19 meters are out all at the same time, there's no way that the other meters magically keep power, especially when they're on the same phase. So it's a pretty obvious conclusion that those meters really belong somewhere else. And sure enough, nearby there was a transformer where only 2 meters out of 24 were affected by the very same outage. In other words, they were out at the same time. And while it's no proof, it's very strong circumstantial evidence that those 2 meters of this transformer with 24 meters really belong to this transformer right here, where 19 of 21 were in outage. For another one, there were 11 out of 12 meters were out, and another transformer within 242 feet had 1 out of 21 meters experienced an outage. And once again, this is strong circumstantial evidence that 1 meter should have been on the original transformer and not on the one that was 242 feet away. This is very low tech. It's strictly it can be automated, of course, and we have. So you get a list of which meters are likely misconnected, and it doesn't require any fancy data. You are simply looking for when the power is out, and you don't even look for power off and power on events. You're simply looking for zero energy, which rarely happens if the meter has power. All the other transformers had very good correspondence between the meters that were connected to it according to utility records. In other words, all these other transformers were either all meters were off or all meters were on during that outage period. Another example was done with a fairly larger outage, 481 meters to 92 transformers. And again, we had one transformer where only 7 out of 8 were in outage, and another one had 1 meter out of 5 by the same outage. And again, this is like almost like shooting fish in a barrel. It's very light. 1411 though, that was the one suspicious thing. That's a little bit far. So I'm not saying this is a slam dunk, but at least we know that in this particular case, the first transformer, that 1 meter out of 8 belongs somewhere else. So with that third example, we come to our concluding slide, where again we've been focusing mostly on how to automate grid topology detection and grid topology maintenance. We all know that meter connectivity and even transformer connectivity does not stay constant over time. So even if you have a perfect records at a particular time, they're likely to gradually get worse over time because things do change and there is a lot of work required, maintenance, storms happen, things have to be rewired in a hurry. So it's important that this kind of monitoring be done on a continuous basis. And that's what we are developing. So all of these methods that I've shown you are actually can be run on a continuous basis. And if you don't hear from them, everything's fine. But if the continuous monitoring finds a change, might find a change, sudden change in an impedance of a meter, which is a red flag. That really, and it's a much better red flag than just a tamper flag. Or if you find that a home affinity suddenly is less than a way affinity for a particular meter, well, in all likelihood, that meter has been moved. And as outages happen, and they always will happen, a post-mortem analysis doesn't cost very much if it's automated. It's something that just happens and just contributes to your database. And all three manners automatically can keep both the grid topology up to date and can also flag potential theft without getting humans involved before you have a fairly high degree of certainty that theft is occurring. And that concludes my formal presentation, and I'd be glad to entertain questions.
Great, thank you, Robert. We do have some questions coming in via the Q&A tool. You can type those in. This is on the top left of your screen. It's click on Q&A. You can type your questions there. I will also unmute everyone's lines here, so you feel free to ask questions aloud. One moment while I do that.
The leader has unmuted your line.
Okay. Oh, the first question is a simple one. Yes, we will post the recording to the webcast up on our landing page, and Robert and I will talk after this webcast, but we should be able to send a PDF to all of those that attended as well. That was an easy one. Let's get a hard question. All right, here we go. Here's a question for you, Robert. Are you looking at instantaneous voltages, or are you looking at the average voltage values over the 5-minute period?
Average voltage over 5 minutes. Thank you for the question.
Okay, and all attendees should be unmuted, so if anyone has questions, feel free to ask those aloud.
Hello?
Yes.
Yeah. So my question is, how consistent is power outage and power restoration exception at this point?
I'm sorry, how consistent?
Right.
Well, when a power outage happens, the meters are very good at sending a power out signal and also a power restore when the power is restored. The problem is that unless you're on a cellular network or on a fixed network, if you are on a mesh network, for example, that power out and will often not reach the head end because it relies on other meters retransmitting. So that's why that's why power outage signals are often inconsistent, or in a way that you do not hear from all meters that are in power outage. There's nothing wrong with the meter. It's the fact that the communication itself is affected by the power outage.
So this is the problem we are experiencing here. We are at the cellular network, RFLAN, and we don't have a consistent outage versus the restoration. So analysis are becoming difficult. So are you guys taking a look into the cellular network of the exceptions being traveled consistently?
Can you define consistent?
Consistent, if I see a meter going through a power outage restoration, I should see an exception at the same time. Once upon a restoration, I should see a power restored exception. But oftentimes what happens, I don't see a power outage, but I would see a power restoration. Right.
Well, that makes sense. Because again, the power out event is often affected by the power outage itself. In other words, it doesn't get transmitted because maybe the power was already out by the time it would have been transmitted. It is a problem, I agree.
Right.
But what we're working on is to be able to live with a incomplete set of power outage signals and still resolve them back to all the customers that are affected, and preferably not just customers, but also transformers and sections.
Right. So I'm just, giving you kind of an example, the situation which we are in right now. So we're kind of having that difficulty which we're going through, but eventually we are leveraging the voltage information for an hourly on an average, and then kind of making a correlation. So it would be great, once we have some resolution on the cellular network, folks, then it would be much helpful. Thank you.
Thank you.
Any further questions? Oh, here we go. Here's another one. Have you done any research as to how much load is currently lost to theft as a percentage of total load?
The short answer is no. I've been really focusing on the detection of it, but it's difficult to get to any actual data as to how much power is lost, almost by definition. And partly it's regulatory because utilities essentially get paid even for power that's lost, as long as it's not excessive, where all the rest of the ratepayers pay for it. But we found a particular need for theft detection in non-U.S. utilities that have much greater problems with power theft. But I do not have actual information as to, I'm sorry, I do know that in places like Brazil, I believe they have like a 30 or 40% power loss in some areas, so they're very much concerned.
Thank you, Robert. Any questions, whether it be Q&A tool or asking out loud?
Can you also use this to estimate the amount of theft there is?
Sorry, the amount of what?
The total amount of theft?
Sure. Oh, yeah. Yeah, because once you find that the voltage drop that you would observe, using the impedance for that meter will give you a direct idea, in fact, a direct quantitative information as to the amount of power that's being taken illicitly at that particular meter.
Okay.
Did I answer your question?
Yes.
Yeah.
Thank you.
Okay, here's another. How about the situations where you have a network of transformers serving several premises? How is the AMI data able to help identify outages in network underground situations?
I'm not sure I totally understand. I mean, it's not unusual for a transformer to serve several premises, and the outage. Anyway, I'm sorry, I don't understand the question.
Okay, perhaps the person that typed that could maybe clarify.
Sorry, that was me typing the question. In some cases, we have, load being shared within few transformers, so you don't have one transformer serving 5 premises. You may have 2 or 3 transformers sharing the load of those premises. And when an outage happens on part of the feeders underground, it kind of becomes difficult. And if the last gasp messages are not all transferred, you can't clearly identify which premises are really out. Have you looked into how AMI could help? Is there anything else other than last gasp that you could look into, like voltages or?
I see. Yes, now I understand. I have not looked into that yet, but we do have a likely installation coming up. I cannot name where exactly that case happens frequently. So I cannot answer you right now on what to do because I don't know yet, but that's certainly something I'm going to be looking into.
Thanks.
Okay. In terms of theft detection, what if the transformer has an unmetered load? Will that unmetered load influence your mode or your model? Excuse me.
By that, I mean if the transformer example has lighting supplied like street lights, for example, the meters themselves will. The issue there is that the meters will experience the same voltage unless, of course, the unmetered load happens along a lateral. So some meters are downstream, some meters are upstream from that lateral. We actually do correct for that by looking at a long-term bias. So if a meter has if a group of meter is consistently half a volt below that of other meters, we correct for that bias, not only because of unmetered loads, but because the absolute voltage measurement in meters, is not likely to be quite that accurate. It would not be unusual to find a systematic error of maybe up to a half volt. So we don't pay much attention to long-term changes like that, but to the short term. Now, if the unmetered load, and that's somewhat related, if a theft, for example, occurred directly on the secondary of a transformer and upstream of all meters, I mean somebody taps directly into the transformer, which does happen, then of course all meters will have a lower voltage. And the only way to find that out is by comparing that transformer secondary voltage to that of other transformers nearby. And if you find a systematic deviation, that is at least an indicator.
Okay, thank you. Were impedances calculated for different services consistent, or was there a wide range?
The range, I showed a chart on the range early on. They tend to be, most of them tend to be in between about 20 and 100 milliohms. And those that were higher would frequently be where the correlation wasn't very good. So you can't really pay too much attention to it. We of course keep track of the margin of error of the impedances and also the R² of the correlation. And if it gets too bad, not all meters will have a consistent measurement of impedance. I'm sorry, not all service drops. For example, if somebody is absent a lot, it's very difficult to get an impedance with this method because there's very little load change. But again, back to the question, a typical range is between about 20 and 100 milliohms that we found.
Great, thank you, Robert. Any other questions before we conclude? Okay, great. Well, thank you everyone for your time attending today. And Robert, thank you for presenting. As I mentioned earlier, we are recording this and we will put the recording of both the slides and audio on our landing page, and we'll get an email out to everyone that's attending with that information. If you have any other questions, please don't hesitate to contact Robert or myself. My name is Becca Jones. And we also have 2 more webcasts in this series. You should have received the email invite for those. Those will take place in February and March, and we hope you can join us for those webcasts as well. Thanks, Robert, and thanks everyone else. Have a great day.
Thank you.
Thank you.